Alright, hello class. Today we're going to be talking about section 3.1, which is the introduction to derivatives. Okay, in fact, all of chapter 3 is on what we call derivatives. Right? And what that basically comes down to is what we'll see. Derivatives are basically, you can think of as rates of change. Right, so as I'm sure I've mentioned before, calculus you can think of as the mathematical study of change, right? So what's going on, how's a function behaving over time, that sort of thing. And derivatives are a main part of that discussion. In fact, for most people, when you think of calculus 1, derivatives are your main topic, right? This is probably the big topic of this class, right? And basically what a derivative is it gives you the rate of change of a function at any point. Now, why might that be useful? Well, if you're, like, say you throw an object, right? Say I drop that pencil, right? At each second, it has a velocity as it's falling down, okay, as it falls towards the table there. And if we have a function that models its position over time, the derivative can give us the velocity or the rate of change of that pencil at any particular second. Okay, that's why this is very useful, okay, because it finally gives us a way to fine-tune or find really accurate calculations for rates of change, okay, given as long as you can find the function. Okay, now as far as rates of change go, so far the big ones we've talked about, or that you've seen before is what I should say, we have linear rates. Right, and that is things like y equals mx plus b. You've seen that before, a linear function. They make a line, right? And this is your constant rate of change. Okay, and another one that you've seen before is an exponential rate, which is more like a constant percent rate of change. Again, that one isn't, well, it is important, but I won't write that one out. But the big one I want to really mention is the linear rates, when you have a constant rate of change. But the problem with the constant rate of change, for example, that would be like saying I was traveling at 75 miles per hour. Okay, so we could say that the distance I traveled was 75 t. Right, so this would be saying that you travel at 75 miles per hour. The problem with this, to give you an example, is say over 2 hours, right, I traveled, and this is the distance, and I traveled, let's say, 150 miles. Okay, so 150 miles traveled over 2 hours. That gives us a rate, right, of, well, we just find the slope of that line, which is going to be 150 over 2, which is 75. And it's going to be miles per hour because we have miles up here, hours down here. Okay. So that's sort of like saying, say I got on the interstate and I, traveled 150 miles in 2 hours. I would tell everyone, well, I traveled at about 75 miles per hour. But here's the real question. Do you ever, when you're driving down the road, do you ever actually travel at exactly 75 miles per hour? Even if you set your cruise control to 75, you're still oscillating around 75, right? You're never actually there. So actually what your distance would look like is probably more like something like this, right? And here's where you got behind somebody who was driving really slow, and then you sped up. Maybe you sped up to pass a semi or something, and you came back down. This is what distances as you travel look like, right? Real life phenomenon, real world functions behave more like this than they do ever a straight line. Okay? But in this example, what I can say is that even though I'm never really traveling at 75 miles per hour exactly, and if I am, it's only for like seconds, right? At this particular second, I'm hitting 75 miles per hour. At this particular second, then it's up to 76. You know, you're oscillating around that velocity, you know, throughout your trip. But even though that's true, we can still say that, well, on average, for that trip, I was traveling at 75 miles per hour, right? No one really wants every single little detail about your trip, right? You don't want to hear about every semi you got stuck behind and then eventually had to pass, so you're slowing down to 60, you're speeding up to 80, slowing down to 60, speeding up to 80. Nobody cares. On average, you traveled at 75 miles per hour, right? So that is what we have for our general everyday function to talk about its rate of change. It's what we call the average rate of change. Okay, so the average rate of change of a function, f of x, from x equals a to x equals b, and sometimes you'll hear me just say from a to b, or you'll actually say on the interval a to b, that's two other ways to say it, is given by this, and this is my made-up notation, but it's basically the average rate of change of f from a to b. And that just gives me something I can write, so I can say average rate of change equals. It's basically f of b minus f of a all over b minus a. Right? And this should look very familiar, not just because you've seen this before in, say, pre-cal or algebra, but also it should look really familiar just from the definition. F's are equivalent to y values, and here's our x values. So we basically have change in y's over change in x's. And that should remind you of slope. And in fact, that's exactly what it is. If I have this function here, right, say this is f of x, and let's say a is here, and let's pick a different place for b. Let's say b is up here. Right. And if I draw a line between these 2 points that I made, right, and I call this line L, the average rate of change is actually the slope of that line L. That line L is called a secant line. Okay. So the average rate of change is basically just a slope, and that brings us back to the linear functions we talked about that had a constant rate of change, right? Because all we're doing here is we're measuring the change of a function, over time, okay? Measuring the change of a function over time, basically just using a line. We just stamp a line onto it and use its slope to tell us what the rate of change on average is of that function. Okay, so let me write some of this down. Okay, so as we said, the average rate of change of f of x is merely the slope of the secant line L, right? So here, our slope m is basically the average rate of change. Okay? And now what is a secant line? Well, a secant line is basically if you take 2 points on the graph of a function, draw a line between those 2 points, you get what is called a secant line. Okay? Now, you might think, well, this seems kind of hand-wavy. Right? This doesn't seem all that legitimate because all we're doing is stamping a line on it, on our function, whatever it might be, and just saying that tells us on average what the function does over time. But actually, this gives a pretty good idea, okay, of what's going on. Let's take a look at this crazy graph here. Right, say we have this odd oscillating graph. Right, it goes up, it goes down, acts crazy. Okay, but on average, right, it's going up and down, increasing, decreasing, kind of going crazy, but on average, what is it doing? Okay, over its entire lifespan. Well, on average, it's increasing, right? So if I say A is, I don't know, right here, and this point here, this Y value is f of A, by the way, and let's say that B, I don't know, is around here, and I draw a line between those 2 points. Here's f of B. That line kind of matches the overall behavior of that graph, right, of this function over time. On average, right, that function is increasing, and at about the same rate as this line is, on average. Okay. Now, that's the best we've been able to do, but it does give a pretty good sense of, you know, what that function's doing over time. But the problem is it doesn't give us enough information, okay? Not for what we want to do, right? For example, what is the actual rate of change at this point right here? Not over, right? Not over the whole life of the function, but just right here. What is the rate of change right there? Or what is the rate of change right at B? Okay. What's the rate of change right at A? Okay. That's the motivating question right here, is what's the rate of change at a particular x value? Okay. So this just gives us the rate of change over an interval, right, over an entire number line. Okay. So this gives the rate over a time period. Okay. How do we find the rate at a particular instant? And that, class, is exactly what the derivatives try to answer. So this is the difference between saying, hey, I traveled, over my entire trip, I traveled at about 75 miles per hour. That's the difference between saying that and looking down at your dashboard at a particular moment and seeing exactly what speed you're driving at that second. Okay, so, you know, I can just tell you I traveled at about 75 miles per hour, but if you call me in the middle of my trip right at, say, noon, and ask how fast I'm driving at that second, I can look at this speedometer and say, oh, I'm going 76 miles per hour at this second. Okay? That's the difference between these two ideas here. Okay? And the answer to this question basically comes from limits, because what someone much smarter than me came up with, they said, well, okay, we have the formula for the average rate of change. How about we look at the average rate of change from A to A? Right? So perhaps the rate at A, right, the actual rate of change at x equals to A, perhaps this can actually be found by looking at the average rate of change from A to A. And think about that. If I calculate the average rate of change from A to A, it's not really an average anymore, is it? The average rate of change from A to A would just be the rate of change at A, right? But here's the problem. when we go to calculate that, say average rate of change of f of x from a to a, right, that's going to be f of a minus f of a all over a minus a. Oh, and that's 0 over 0, which is undefined. Okay, so up until now, we'd be screwed, right? There'd be nothing we could do. We'd be finished. The average rate of change from A to A is undefined. But what have we done before when we had cases like this? Well, we looked at the limit. Okay, so yes, we can't just take the average rate of change from A to A, but since we already have the average rate of change, perhaps, right, we can take the limit. And it will exist. And if that's the case, well, that must be the rate at x equals a, right? If the limit exists, that means the average rate of change is getting closer and closer and closer to this particular rate, right? As the distance between a and whatever you're going to, a and b, as b gets closer and closer to a, it must be getting, those averages must be getting closer and closer to the actual rate. Okay, so let's write this definition down. Okay, so this motivating question has brought us to this definition here. The instantaneous rate of change is what we call it. So the instantaneous rate of change of f of x at x equals a is given by this limit. We take the limit as b goes to a of f of b minus f of a all over b minus a. It's essentially just the limit as b goes to a of the average rate of change of f of x from a to b, right? And we're letting b get closer and closer and closer and closer and closer to a. So for those of you who are maybe wondering where the limit is useful, it's here. Okay, it's the fact that we can actually find the instantaneous rate of change of a function at a point using the average rate of change and just shrinking it down, okay? Shrinking the interval down. Right? And this is one definition. We actually have a better one. Okay, the one you'll see usually is actually the limit as h goes to 0 of f of a plus h minus f of a all over h. Okay. And this is the one that is actually used most. Every once in a while you'll see this one used with the limit as b goes to a, but more than likely the instantaneous rate of change of f at a is given by this limit here. The limit as h goes to 0 of f of a plus h minus f of a all over h. So let me real quick show what's going on with this definition and why it's actually the same. Okay, so if we actually consider the average rate of change from x equals a to x equals a plus h, and we plug it into our usual formula for the average rate of change from a to a plus h of f of x, we actually get the top, is what we saw in that other definition I showed you, f of a plus h minus f of a, right? This is our b. And then over b, which is our a plus h minus a, and it comes out to be f of a plus h minus f of a all over h. Okay, so this is just another way to write the average rate of change, and here's how it does it, right? If I have my function here, and let's say this is a, right? A plus h, let's say, is right here. So this y value up here would give me f of a plus h. This would be f of a. And we have the secant line between the two. And this right here, this distance between A and A plus H is H. So what this particular way of writing it does is it actually rewrites the average rate of change in terms of the distance between A and A plus H, the length of the interval. Right? So it's just basically just the average rate of change written in terms of the length of this interval. A to A plus H, or B if you like. Okay. So what's really happening, if we go back to this definition, if H is the length of the interval, what we're doing is we're shrinking the interval down to 0. So let me write that, shrinking the interval to 0. So what we're basically doing is here's, an interval H, here's H sub 1, let's say, and we get a new secant line and an H of 2, and we get another secant line, an H3, or I should be saying this is A plus, but hopefully you gather what I mean. And we get another secant line, and it's gotten really cramped in here, but hopefully you can see that of these lines I'm drawing, they start to get closer and closer to a particular line themselves. Okay, so hang on, let me draw another graph for you. Okay, so this is not necessarily the best graph of all time, but here's A, here's f of A, and I'm going to start drawing some secant lines, and you can see I already have this big green line here. All right, so let's draw this secant line. All right, so there's the first one I'm going to draw. And then let's cut the interval in half. Right, so we'll cut it in half and draw another secant line, and maybe I can do this one in red. Okay, and then let's cut the interval in half again to give me an A plus H3. Maybe I can do this line in red as well. Just going to clutter up my red a bit, but okay. And then we'll do it again, cut the interval in half, make another line. Well, hard to see what's going on here, but hopefully, and let's make this one in black. It's a little hard to see from my graph, but everyone see that these lines are getting closer and closer to this green one as I make these secant lines. What's happening is that the graphical representation of the average rate of change is the secant line, right? Well, the slope of the secant line. And as we take the limit, right, as we let those intervals shrink down to 0, those secant lines get closer and closer and closer to this other line, this green line, which is what we call a tangent line. So, as h goes to 0, right, the length of that interval goes to 0, the secant lines get closer and closer to a line called the tangent line. Right, so that's something to keep in mind here, is that the instantaneous rate of change, which I'm just going to say IRC here, is actually also, right, the slope of the tangent line. Okay, so if this is at x equals a, this will be the slope of the tangent line at x equals a. So a lot of students tend to worry about drawing tangent lines. There are problems that ask you to draw tangent lines. We will look at also calculating how to find the equations of tangent lines. But to start with, basically what you need to know, and this is a great time to go to your book and look at some pictures, because the book draws far better pictures of tangent lines than I do, and I could prepare some pictures with tangent lines, but honestly your book does a far better job than I probably could. But basically where it comes from, that word's probably familiar because, you know, if you go back to geometry and you look at your circles, the tangent line of the circle was a line that crossed the circle once and only once. And you see how it just kind of skims off that? Well, that's kind of how they work here. If I were to put one here, it kind of skims off the graph like that. Okay. It's like you try to let where the line is drawn kind of match what the graph is doing itself, right? You try and almost flatten it, try to make the line and the function equal, or the slope and the function match each other at that point. And some definitions will say it's a place where the line will only touch the function at one point, but that's actually a bad definition. One thing you can always do if you have trouble is just draw a secant line really close. Right? So for example, if I wanted to do one here, I'd put a point right here and draw the line between those 2 points, and that pretty much gives me what the tangent line basically is. I'm basically drawing a secant line really damn close to that point that I'm looking at. Yeah, fair enough. And it has to work on both sides too, so if you're looking at this point, you could put a point here and a point here and draw a line between those 3 points. Now, pretend your drawing skills are better than mine, and I just bollocks that up. But yeah, put the 2 points together and draw a line as best you can. I'm not looking for perfection here, but I don't want to see something like this because that's clearly not what's going on here. Another way to think of it, I like to tell my students, is that, remember, these things are telling us the rate of change, and I always think of it as it kind of gives a direction too. If this were a roller coaster and we were speeding along the roller coaster and suddenly the rest of it disappeared, we would actually be heading, like if it stopped right here, we'd be heading off in this direction. Right? That's kind of the direction of the rate that we're going. And if you think of it coming around this way, you fly off in that direction. Okay? That's kind of what the tangent lines do, is they it's almost like they point in the direction you'd be flying if this was a roller coaster and it disappeared at that moment, right? You flew off the track at that moment, you'd be heading in that direction. That's not exactly what tangent lines and the derivative actually gives you, but it helps me draw them. Okay, so let's actually move on to a physical example here. There's a lot of abstract explanations going on here, and the instantaneous rate of change, where that comes from, is fairly abstract. I mean, you're taking the average rate of change on smaller and smaller and smaller and smaller intervals. Eventually, you're looking at, say, the average rate of change from 1 to 1.000000000, you know, ad infinitum, and then throw in a 1. But let's actually look at something concrete so that it can help us kind of put this in the real world for us. I always like to use physics examples to start this stuff off, mainly because we all understand miles per hour, feet per second, that sort of thing, right? When you're in a car, you travel a certain distance over a certain time. You know, you look at the speedometer, there's your miles per hour. Okay, we all kind of understand how that works. So I'm going to start with just a very simple physics problem here. Of a rock is dropped from an initial height of 100 feet, and the height of the rock at t seconds is given by s of t is equal to, did I say, yeah, the height of the rock in feet. I should specify there, just so. Anyway, is s of t is equal to 100 minus 16t squared. Those of you who know your basic physics, you know that that 100 is your initial height, and the negative 16t squared, that's basically your gravity term. Right? There's no initial velocity, we're just dropping the rock, so it's not like we're tossing it up in the air or firing it from a catapult or anything like that. We're just dropping it. Okay. Now, first, let's find the average rate of change of the rock in the first second. All right, and that's a special way of just saying from t equals 0 to t equals 1. Right? That's what that's saying. Then part B, it's asking the same thing, but in the next second. So another way to say that would be in the second, which is always kind of fun to say. Or this is from t equals 1 to t equals 2. I wrote it this way intentionally, right, because often that's how the book will write things. And then find the instantaneous rate of change of the rock at t equals 1 second. Okay, so let's start here at part A. We're going to find the average rate of change of the rock in the first second. So we'll start, right, we'll look at the average rate of change of s of t from 0 to 1. Now writing this is actually optional, but I like having something to write. Just, makes me feel a little better. So remember, the average rate of change is, here we can go back to the definition, if you like, if I can find it. Wasting time. Here we go. Average rate of change is your f of b minus f of a all over b minus a. All right, so for the actual average rate of change, we don't have to take the limit here. It's just the average. All right, so what you pick as your b and what you pick as your a isn't really that important, provided you stay consistent. Okay. So it's going to be s of 1 minus s of 0 all over 1 minus 0. So if you remember what s is, it's 100 minus 16t squared. Okay, so s of 1 will be 100 minus 16, 1 squared. Okay, and then it will be minus, so here's your s of 1, minus 100 minus 16, 0 squared. Okay. And this is your s of 0. I probably should have actually put this down here, so actually let me do that just so it looks a little better. 100 minus 16 times 1 squared, and let me put that in parentheses, minus 100 minus 16, 0 squared, all over 1 minus 0 is just going to be 1. Right, so we'll just ignore that up here. Okay, so we're going to get 100 minus 16 minus, that's 0, so minus 100, we get negative 16. Now the question is, negative 16 what? And here's where it's very helpful to know what everything is. If you guessed feet per second, or you knew it was feet per second, very good. But if you ever have trouble interpreting what units this should be in, well, what are the units of s? It's in feet. What are the units of t down here? It's in seconds, right? We have a fraction, feet per second. That's our units at the end. Okay? Now, the next question is, what does this actually mean? Does it mean that the rock is always falling or changing at negative 16 feet per second? No. Okay. Basically, the negative means it's falling, and what this tells us is that in the first second, okay, the rock is falling we can put it here, on average at about 16 feet per second. There are a lot of ways you could word this. You could say the rock falls at 16 feet per second on average in the first second. Right? There's a lot of ways to do this. But basically what you're looking for is that it's on average. Right? The rock isn't always falling at that rate. Okay? Just in between t equals 0 and t equals 1. All right, let's look at part B. That's in the second. That's always fun to say. But now it's going to be the average rate of change of s of t from t equals 1 to 2. Okay, so that's going to be s of 2 minus s of 1 all over 2 minus 1. Okay, so when we calculate that out, remember s is 100 minus 16t squared. So this will be 100 minus 16t squared. I recommend putting both of these pieces in parentheses, otherwise you might mess things up because this piece, whoops, and we know what our t is. Sorry, that's 2 squared. Okay, and so this will be 100 minus 16 times 1 squared, all over 1. Now, to continue this, sorry, camera issue of some kind. To complete this, we're just going to crank out this value, right? So that's going to be 100 minus 16 times 4, which will be 64. And then be sure to distribute this negative sign across. That's why it's very important to put this in parentheses. So this will be negative or minus 100 plus 16. Right, and the 100s cancel, and that's actually a very common step here. Any constant that you have in your functions will actually cancel out each time. Okay, and so what we'll end up with is, should be negative 48. Okay, so negative 48 what? Feet per second. Okay, so on average, between t equals 1 to t equals 2, the rock is falling by negative, whoops, I shouldn't put negative in there because I already say it's falling, by 48 feet per second. So where that negative comes from, if I just asked what the velocity was, you could say it's negative 48 feet per second. If you were trying to say what was happening in real life, you would say that the rock is falling because you have a negative velocity. Right? And once you say it's falling, you don't have to put the negative back in there. Right? Okay, so that's the average rate of change in the next second, or in the second second. Okay. Now, let's look at part C, which is finding the instantaneous rate of change of the rock at t equals 1 second. Okay, so let's calculate that instantaneous rate of change. So the instantaneous rate of change of s of t at t equals 1. Well, let's go back to what our definition of that was. Remember, that's going to be the limit as h goes to 0 of f of a plus h. A here is going to be 1, right, because that's what we're looking at, minus f of a all over h. Okay, so this is going to be the limit as h goes to 0, f of 1 plus h minus f of 1 all over h. And we're going to calculate this limit. Right, so you'll have trouble doing this if you don't remember how to calculate limits. Okay, so this will be the limit as h goes to 0 of, remember what our function was? Oh, and I wrote f's here. These should be s's. My bad. This was 100 minus 16t squared. So this will be 100 minus 16 times 1 plus h squared. Then minus 100 minus 16 times 1 squared. All over h. Okay, so this is where that, you probably remember this from that review problem set I gave you guys. Okay, and then we're just going to expand all this out. Right, so this will be the limit as h goes to 0, okay, of 100 minus 16. I'm going to FOIL this out. That'll be 1 plus 2h plus h squared minus 100 plus 16. Remember to distribute this negative sign across. That's the biggest problem I see, biggest mistake I see people make. Okay, and check this out. The 100s cancel again. If this doesn't happen, okay, if you don't see constants cancel out, you have done something wrong. In fact, whenever you're calculating the instantaneous rate of change like this, using the limit definition, you should have a lot of stuff just cancel out and be left with only h's. We're going to see that here, because now when I distribute this negative 16, I'll get negative 16 minus 32h minus 16h squared plus 16, and check that out, there's another, and it's all over h of course, there's another set of constants that cancel out, and we are only left with h's here. Okay, so we get the limit as h goes to 0 of negative 32h minus 16h squared all over h. Whenever you're calculating the instantaneous rate of change using the limit definition here, this should pretty much always happen. You should always get down to a term or a step where all you have is h's in the numerator. If you don't get that, this is a flag. This is a place where you can check. Right? This is a checkpoint. If you don't get that, you've done something wrong, provided you started with some nice polynomial. Okay? In most cases, you get down to here and you had some constants that didn't cancel out, you've done something wrong. Go back and look at what you did. This is where a lot of people mess up, because then they try to cancel this when really they made a mistake up here. Okay? So what we're going to do is factor out the h in the top. Now a lot of people already know how to cancel that the h's, but I always recommend, if you're unsure, just factor. If you can factor the top, you can cancel the h's. Okay, and I guess I should mention that the reason we're doing this in the first place is because you can't just plug in 0. Right? If you were to just plug in 0, you get s of 1 minus s of 1, which would be 0 over 0. So since this is a 0 over 0 case, it involves calculating things out, simplifying, and all that jazz. So the h's cancel, and we get to, this is the limit as h goes to 0 of negative 32 minus 16h. And as h goes to 0, well, negative 16h goes to 0. So the whole thing goes to negative 32. Negative 32 what? Feet per second, of course. Now what does this mean? Okay, what this means is that the rock at t equals 1 second, so at the 1 second mark, okay, it's traveling at 32 feet per second. Is it always traveling at 32 feet per second? No, right? It started off at 0, right, traveling at 0 feet per second, because the second we let it go, gravity has just started pulling on it. It had no initial velocity, so it starts by falling at 0 feet per second. And then at 1 second, it's falling at 32 feet per second. So at t equals 1 second, the rock is falling at 32 feet per second. Okay? So that's the difference there between the average rate of change and the instantaneous rate of change, is the difference between what is happening over an entire second and what is happening at an instant. Alright, so in the first second, we found that the rock was falling at about an average of 16 feet per second, and then in the next second, from 1 to 2, we found that the rock was falling at about 48 feet per second. So mathematically, what have we just shown in part A and B? We've shown that the rock is speeding up, right? In the first second, it traveled at about an average of 16 feet per second. In the next second, it's traveling at an average of 48 feet per second. It's speeding up. We already knew that. Okay? We already knew that just from what we know about physics, that if we drop a rock off a cliff, it's going to speed up and speed up and speed up and speed up until it hits the ground. Okay? And so I wanted to mention that before we look at the graph, which I drew here. Here's a kind of exaggerated, not to scale graph. Okay. But what we have here, here's 1 second, 2 seconds. Here's the height, s. Here's the time, t, in seconds. And that first thing we calculated was the average rate of change between 0 and 1. So that would be this secant line. Right, in this secant line, we found that its slope was negative 16. Well, we see graphically that it is a negative slope. Right? And it's not really drawn to scale, so it's kind of hard to tell what's going on. But if I look at the secant line between 1 and 2, well, we found that the slope of this line, the average rate of change, was negative 48. This line that we got here from the secant line is actually steeper. Exactly what we would expect. It's traveling at a faster rate. Okay. And the instantaneous rate of change, we actually have this tangent line here. Right. We found the slope of the tangent line at t equals 1 was, what, negative 32? So that is graphically what we found, and it actually seems to match. Now I draw a tangent line at that point. It seems trapped between the other two tangent lines. The first one we found is shallower than the second one. Right? So graphically, mathematically, we have actually just shown what we know to be true through physics. Okay. So that is the first part of section 3.1. Next, we'll be looking at trying to refine this idea a little bit more, because what if I said that now I wanted to find the instantaneous rate of change of f of x at 2? Right, if I said that, we would have to go through all of that work again. So that's the next thing that we'll be looking at. And it will probably have to be in the next lecture for us to do that, since we're already hitting the 50-minute mark. So we will discuss that then. Cheers.